Okay guys, so for the two examples I want to work, the first one's this cantilever. It's got a cantilever portion, a normal span, simple span, what we would call simple span, and then a downward point load. So we're going to start from left to right, and we're going to cut sections along the way and develop the shear and moment diagrams for this. Okay, so I just added dimensions because I forgot those. And so let's start. So the first thing we're going to do is we need to find the external reactions, because that's going to relate to our shears, which will influence our moment. But before we do that, let me just draw what they're going to look like at the end, so you have the end in mind, and then we'll work towards the end. Okay, so I'm going to take this piece of fodder here. That's my beam. The shear diagram is going to look like this. So with the support, it'll change shape because there's a reaction there. And it'll remain constant to here. And then it'll come up to this. And when we do the whole thing, this should calculate to 0. If it doesn't, then we know we have a mistake. Alright, moment diagram is going to look something, let's see, it's going to look like this. Kind of something like this. We'll figure that part out. But there'll be some high point right over this support, and then it'll come. Well, if that is, let's see, if that's an area, that's going to push it down on a linear direction. And then when it gets to here, it'll go up linearly. So let me just shade that in. So it's going to be that and that for the moment diagram. All right, let's get to the numbers. So, like I said, the first thing we need to do is solve for the reactions here. So to do that, we're going to use a free body diagram that only works for the reaction. So we're going to take this distributed load, turn it into a point load, calc reactions, but then when we go to do the moment and shear diagrams, we're going to make sure we use this. If we don't, our shear and moment diagram will look different. And not different's bad, but they'll be incorrect, which is not what we want. So I'm going to redraw. So this is my load diagram. Let's call this load for, let's see, for reactions. Okay, so then I'm going to have our left, and right here I'm going to have reaction right. And then I'll have this 25 kip load. Okay. Alright, so with that said, let's sum moments about the left. So summing moments about the left equals 0. From here to here, this is 3 feet, so it's half of the 6 feet here. And then from here to here, it's 10, and then from here to there, it's 15 feet. Alright, so sum of moments about this point, I have, I didn't calc this, 2 kips per foot times 6 feet. So 6 comes from here, the 2 kips per foot there, those guys cancel. So that's 12 kip force. So I'm going to say I have a 12 kip force times 3 feet. If I follow my fingers around that, my thumb points up. So I'm going to say that's positive. So 12 kips times 3 feet. This doesn't do anything. That is 25 kips, and that's downward. So minus 25 kips times 10 feet from here. And then I have my reaction at R going upward as positive. So it's clockwise, counterclockwise moment is positive. So I have r sub r times 10 plus 5 of 15 feet r sub r, and that's equals 0. Okay, so make sure, I'm noticing a number of you, as we're working out problems together, is you're getting confused about what the moment arm is. So if I'm summing moments about this point, my moment arm dimension is from this point to whatever I'm doing. So if I go to here, it's 10 feet, to here it's 15. If I went over to here, it would be whatever length that is, but it's all relative to here. From here, going to the end, it's 6 feet. To the middle of that, it's 3 feet. So everything's relative to this. If I were to sum moments about here, it would be 5 feet to here, 10 feet to here, and 16 feet to here. And then from here, would it be from here to here would be that plus that plus that. So wherever you sum moments about, that's your datum or your base point for all of the moment calculations. Okay, so back to this. Let me just start breaking this down. So I'm going to have, let's just do that here. So let's see. 12 times 3, 25, 10 minus, that's going to go to the other side. So I have minus 214 kip feet plus 15 feet. R equals 0. This is going to come over to here. Divide by 15 on each side. And RR is going to be this divided by that, essentially. 214 divided by 15, that's 14.26. Okay. Now, I'm going to do some moments about the right-hand side now, over here. And then I'll do sum of forces in the y to check myself, just to be a little extra thorough. There's nothing worse than having a professor give you a wrong problem that you don't understand what mistake they've made. So let's not do that. Alright, sum of moments about this point here. So I've got 25 kips times 5 feet. And that is going clockwise, so 25 kips times 5 feet. The next force as I move it along is RL, and that's negative because it's going clockwise, so R sub L times this length plus that length of 15 feet. Oops. And then the next one is also negative because it's making, no, that would be positive, thumb up. So got 12 kips times its moment arm, which is going to be 5 plus 10 plus half of 6. So what's that? 10, 15, 20, or 18 feet. Alright, so I'm going to take that, add it to that, move this to the other side so it gets positive, divide that plus that by 15 feet. So I will just skip an intermediate step and do all of this right now. Make sure I do that right. 22.73 kips. Okay, so that's right. So let's do sum of forces in the y direction just to see if everything's cool. So sum of forces in y equals 0. So if I come to my free body diagram, I've got 12 kips plus 25 kips downward, and then I have the right and left reactions upward. So I'm going to set those equal to each other. So 12 kips plus 25 kips. So that's this guy plus that guy. That should equal this guy plus this guy. So we'll see if that's true. So 12 plus 25, that's going to be 37 kips. 22.73, 14.26. 36.99 for an engineer. That is 37. Okay, rad. Alright, I'm going to start another video so this thing doesn't get too long. And then we'll keep at it. Okay, so now I want to come back to this free body diagram, and I want to draw in and write in the magnitude of my reactions. So write R sub R coming from here, 14.26 kips, and the other one's 22.73 kips. It makes sense that this guy is bigger because it's taken all of this and some of this. So that's logical. Plus we checked at sum of moments or sum of forces and Y, which equaled everything balanced out. So we know we're good to go. Alright, so flip that around. Let's do this. So the next thing I want to do is if I do a free body diagram of this point right here with zero, like literally at the end here, let's just do a thought experiment. If the length here of my free body diagram is 0, 0 times 2 kips per foot is 0, so my shear here is 0. Same deal for moment. If the shear is 0, the moment's 0. So at the very, very, very end of this, the shear and moment are both 0, which is logical because nothing's touching it out here. If this were to not be 0 here, there'd have to be something touching it. But since there's not, we don't have to worry about it. So let's do a free body diagram cutting right here at 3 feet. So basically, if I keep with my scale, roughly, hopefully more or less. So if this is my chunk of beam here, and it has a load on it, when this gets cut, from our discussion the other day, I have a shear, a moment, and an axial force. Because there's no axial force externally, there won't be one internally. There will be axial stress, but we'll talk about that in a couple weeks. But the free body diagram at 3 feet is this 2 kips per foot. There's a moment, and we'll call that M3 and a V3 the subscript we'll say relates to the length from the left end. Alright, well this is going to be a little hard to solve with a distributed load, so let's make this a point load, and this thing P3 is going to equal 2 kips per foot times 3 feet. Those go away, I'm left with kips, and it's equal to 6 kips. That's my downward force. So if I do sum of forces in the Y equals 0, I have minus P3 plus V3 equals 0, which basically tells me P3 equals V3, and if P3 is 6 kips, then V3 is equal to 6 kips. Pretty simple. Doesn't need to be more complicated than that. Alright, let's do sum of moments about this point, because the V3 will go away, which will be nice. Or we could sum moments about here. But let's just do sum of moments about this point right here. So M3 is going counterclockwise, so that's negative. And then P3 times its moment arm, and its moment arm, if this is 3 feet, half of that is 1.5 feet. Equals 0. If I pull the moment 3 to the other side, it becomes positive. So it's going to be P3 times 1.5. We know P3 is 6 kips, 1.5 feet. So we have 6 times 1.5, so 9 kip feet. You'll notice I use a HP calculator. That's just how it goes. It's the best calculator out in the world, and if anyone needs a longer discussion on why this is the best engineering calculator, you just come talk to me. All right, let's do the next one. So let's do a cut here, just barely, oh, that's hard to see, just barely to the left of the reaction. And what that will do is get us the shear right before the reaction, then we'll do a cut right past it. So we're going to call it 6 feet, but we're not going to say it's past. It's 1/1000th of an inch to the left of this. And you'll see why in just a sec, but let's go ahead and undo that. I'm going to fold this paper. Okay, so let's do the next one. We'll draw our free body diagram. Now it comes to here. I like to draw proportionally. It helps me keep track of things a little bit better. So here I have 2 kips per foot. And I'm going to draw the resultant in. Well, let's see, we're going to call that P at 6 feet. That's going to be equal to 6 feet times 2 kips per foot. Feet go away, I've got 12 kip feet, or kips rather, left over. So this is equal to 12 kips. At this end, I have a moment. We're going to call that moment 6. And let's call this V6. But because I'm 1/1000th of an inch to the left of this, I don't have to include this guy in this discussion. So let's keep going. So sum of forces in Y, I have 12 kips equals V6. So now I'm starting to just skip some steps. This is the only force down, this is the only force up, so they have to be equal. And then moment at 6 is going to be 12 kips times the moment arm, which is half of 6 feet. So I'll just write 6 feet over 2. So what's that? 3 times 12 is 36 kip feet. Now if I did this right, these should be double our first one, which was halfway along the length here. So my shear, this is 6, that's 12. This is 9. Why is that? Something's weird up here. Or did I screw something else up? Alright, hang on, I gotta look at this. Oh, my bad, didn't need to be double. So here the force is 6 and the moment arm is 1.5. Here the force doubles and the moment arm doubles, so it's actually a quadruple effect. So hence the 36. Okay. Moving on, let's do the free body diagram. So we've done one here, we've done one just barely to the left of that. Let's do one just barely to the right. So 1/1000th to the left, 1/1000th to the right. We're going to still keep the length as 6 kips, but our free body diagram changes a little bit. So let's draw this guy in here again. I've got we have our load here of 2 kips per foot. This is 6 feet. But now we have this upward force of 22.73 kips, which is our reaction. So 22.73 kips, and then I also have a moment. And I'm going to write in our resultant in red. So I'm not going to use this and this. I'm either going to use the distributed load or the resultant, but not both at the same time. And we know P6 equals 12 kips, because again, I'm only going 1/1000th of an inch past, and for all intents and purposes, it's 6 feet. Okay, so moment at 6 is the same thing, because my moment arm didn't change. It's still 3 feet. My load's 12 kips. So I have 36 kip feet for my moment. But now let's do some of the forces in the X, or Y rather, goes to 0. So we have 12 kips down. And this time we have 22.73 kips up. And we also, I didn't draw this in originally, I should have done that. We have a shear force down. So I'll say minus V is equal to 0. So now when I do the math here, V will come over here, this will subtract from here. So I'm going to have shear is equal to 22.73 minus 12, so that's kind of easy to do. That's 10.73 kips is the shear. So what happens as we cross a support, we have a huge, basically a huge shear that gets introduced into the system. Or another way to think about it is that that shear comes out of the system and changes the direction of shear. So if I want to pause for a minute, let me grab some fodder, hang on. Okay, so if I pause for a minute and just draw the shear diagram, I can plot, let's see here. Let's plot 2 points of our shear. We have a 6 kip shear, we have a 12 kip shear, and a 10.73 kip shear. So we would have a 12, or a 6, 12, and then a 10.3. So our shear is looking like this now. And it's going to be constant. Anyway, so let's keep after this. Let's do a new sheet. And now that we looked at this up to this point, let's do another section. Let's cut another section right here at the halfway point of 10 feet and just see what we have. Again, it's just taking a little piece at a time. We're only going to solve one part of this at a time, otherwise our heads might explode, and that's not what we're after. Okay, so I have a reaction here, 22.73 kips. Where I cut through here, I'm going to have a moment. So we're going to call that 6 plus 5, which I guess is still 11. We don't know what that is. We're going to have a shear, but we also have to have this stuff back here. And we can represent that, yes, we can represent that as a force. And if we go back to our previous notes, we know that that's 12 kips. So this is 3 feet, 5 feet. So let's do sum of moments first for the heck of it. Doesn't matter which one. So if I do sum of moments about here, this shear is 0, has 0 effect on the moment. I have this times 5, and I have that times 8 is equal to my moment. So I'm drawing the moment this way, which is negative. And then this moment, this force rather, makes the moment in that same direction. So we're going to also say that's negative. And its moment arm is 5 feet. And then this guy is going the other way. So we're going to say that's positive. So it's 12 kips times 5 plus 3 is 8 feet equals 0. I'm going to, let's see, so let's move the moment over to here. It makes it positive, and then write that on the left. And then I'm going to have this minus that, and we'll see what number we get. Let's see if I can put that somewhere well. So 22.73 times 5 times, and that's actually subtracted. So I end up with negative 17.65 kip feet. Okay. All right, let's keep going. So let's do this. Do a point right here, 1/1000 of an inch left of 25 kips. So let's draw our new free body diagram. And this is starting to get a little burdensome because we're getting further to the right, but we can handle it. So because I'm to the left of this guy, it doesn't show up in my free body diagram yet. So I have this. I have 12 kips. The stuff we just did right here doesn't matter because that's internal. And now we have a moment, so we'll call that moment at 16. And a shear at 16. So summing moments, that's going to be pretty easy because that's 10, that's 3 feet from here to here and here to here. So let's do sum of moments. So I'm going to do this a little differently. I'm going to say if it's a negative moment, I put it on the left-hand side. And if it's positive, I put it on the right side. So I have M16, it's negative. This is a negative effect. 0.73 kips times 10 feet. And then that equals the positive moments going around this way. So 12 kips times 10 plus 3, so that would be 13. 12 kips times 13 feet. I'm going to move this over to here and make that negative, and then solve for this. So if I cross that out, 22.73 times 10. Let's just crank that out really quick. I have negative 71.3 feet, which this is making sense because a negative moment's below the line. It smiles at you, and anyway, we'll see it when we draw it. All right, let's do sum of forces in Y. So we have, I'm going to put all the downward forces on the left and all the upward on the right. So I have 12 kips down, 22.73 kips up, plus V16. So V16 is equal to this minus that. So it's going to be negative 10.73 kips, which it seemed like we, oh, I know why. That's right. Okay, cool. All right, let's keep going. Let's look just to the right of this, and if we remember when we did this, the moment stayed the same, and the only difference is we added the shear. That was negative, so V at 16 plus, we'll call that 16 minus, is going to be, let's see, or hang on, this is, my signs are, I'm being a little sloppy with my signs, so let me figure this out really quick. Alright, so apparently at 7:30 at night my brain works less well than in the morning. Okay, so because this is negative 10.73 and I drew my arrow up, it's really a downward shear. So when I come to, that's like 10.73 here. When I come here, I add, or take a negative 25 to that. So in the end, I'm going to subtract 25, or 10.73 from 25. 25, 10.73, so 14.27. And you'll notice right offhand that equals our reaction, which tells us we're correct because from this point to here there's no change in shear because there's no load. So that's a happy moment in any shear and moment diagram. Okay, so just to reiterate, we've calculated the moment here, which was 71.3 kip feet. And then we calc the shear on both sides. So on one side it was 10.73 and on the other it was 14.7. So the last thing we can do is just, well, I guess we could do one here. Let's do that, but we're going to do it from the right hand side. That'll be easier. Alright, so let's do that. Let's do a free body diagram of the right here. So it's going to be this, 14.26 kips. There's going to be a shear that way and a moment that way. So we'll call that moment at whatever, and then this is the shear. So sum of forces in Y, the shear in that, those are the only two forces, so that shear equals that. 26 kips, and then moment, this moment arm is going to be 2.5 feet, half of this. So moment is just 14.26 times 2.5. And it looks like I drew that arrow wrong, so we're going to call it that way. So 14.26 times 25 is, oh, that's 2.5. Okay, 35.65 kip feet is there, and then when I get to the end here, my moment arm is 0, so my moment is 0, which is how it should be at a pin, because a pin can't transmit moment. Okay, so with all that, now we're going to draw the moment diagram for this thing. So we need to go back through and collect all of our points, well, all of our data points. So we're going to have kind of these lines. Oh, that's going to be sloppy. Hang on. So we'll just project down off of the calc paper here. Alright, so let's start back at the very beginning of this mess. And I come here at the first point. We decided there's no shear and no moment. So I'm going to draw a line for the shear and a line here for the moment. And I'm going to project down off of this. So I come here to my first free body diagram. We talked about this being 0 moment, 0 shear, so I'm starting here for both of these. Then I go 3 feet over, so that's, grab a pencil here, so I come over to about there, and I decided, or we just calculated our shear is 6 kips. And I'm going to draw this as negative because this shear is going down. And then we calc that our moment was 9 kip feet. I'm going to draw that positive because that's how it should be. Okay, so then we go to our next free body diagram, and we had a 6 foot length, which corresponds to this location right there. So I had a moment of 36 kip feet, which proportionally, let's draw like this. And then I had a shear of 12 kips, so we're going to draw that here. I drew these a little too close to each other, but oh well. And then the moment's going to look like that. Okay, so that's that page. And then I come here to my point 11, which was this guy. So that's going to correspond, let me grab a pencil, to that. So, oh, one more thing. When we did this, let me see here, where are we? Oh yeah, when we came just to the right here, we had a change in shear that put us up to 10.73 kips. So that's going to put us up right here. So from this point to this point, it's a total of the reaction. So from here to here ought to be 22.73. So that's 10.73. Alright, then we come to this one, which is at point 11, 11 feet. Our moment was 17.65 kip feet, so this is dropping roughly half of that. And the shear, what is the shear? Oh, the shear didn't change, so it's the same. So This is constant here. This is going to be coming down. Oh wait, that's a straight line. Alright, then we go to point 16, which correlates to that point load where it's applied. And the shear is constant up until that point, but then when we get there, based on our calculations here, our shear is 10.73 on one side and 14.7 or 27 on the other side. So it's going to drop down to here. And then our moment, 71.3 kip feet. And that has gone negative, so I didn't draw the slope of this quite steep enough. Okay, and then we had one more solution at this point right here. So I'm going to come down, and I have a shear which remains unchanged, so it's 14.27 or 26. In my moment, we calculated 35.65. So that's going to go to there. And then we know at the end here it's a pin, the moment's 0, so that has to close. And then here our reaction is 14.27, so I come to here, and that pushes me back up, and that closes. Okay. Alright, that's kind of a little on the complicated side, but that's how shear and moment diagrams are. Fortunately for you guys, you'll be doing this if you stay in a structural or mechanics track. You'll be doing this a lot, so you'll get good at it. Alright, so that was the brute force free body diagram method of doing this. Let me just run through the area method a little, just to make this just close the loop. So if I have a distributed load, anywhere along here I can find the shear by finding the area of that load. So if I come to 3 feet here, I can calc the area of that, which is just 3 times 2, which is 6 kips, and so that corresponds to here. I could come to this point at 9, or at, let's see, 4.5 feet, and multiply 4.5 times 2, and that'd be 9 kips and 12 kips. So the area of this gives me the magnitude at any location of x being horizontal. Then when I come to a support, I have an immediate change in shear, or a point load, which jumps me up, which is just going to be the 22.73 minus the 12 to get the magnitude. And then from this point to this point, there's no load, so there's no change in shear, so it stays constant. When I hit the 25 kips, I drop down, so it's 25 kips minus 10.73, and that gives me that magnitude. And then from here to here, there's no change, so the shear is constant. And then I hit a load, or reaction, and it brings me up 14.26 kips. So this reaction and the last shear should be equal. Alright, for moments, now I'm taking the area of the shear diagram, and that's why this is a parabola, because this is a triangle. So I could come out here to any point along, multiply this magnitude by its correlating distance, divide it by 2 since it's a triangle, and that would give me the point. So I can do this at any point along here. Same thing here, and the reason this is a line, a straight line, is because this is a rectangle, so it's kind of like this to here, this to this. So I can come anywhere along here, calculate that area. So let's say I chose that point, that would be my moment at that point. The only time a moment diagram will have a jump like the shear diagram is if there's a moment on the beam. Sorry, didn't see that. moment on the beam. So if this was the case, then I would come down to where that moment's applied, and that would give me a jump in the moment diagram. But that's not what we have. Anyway, so I keep taking the area of this, and where the shear changes shape, the moment, or it goes from positive to negative, the moment diagram changes from a positive increase, or an increasing to a decreasing, or a decreasing to an increasing, however you see it. So bottom line is, the way I just showed you, it's kind of a brute force method of doing it. When this stuff gets a little more elegant, it's not very elegant, but if it gets slightly more elegant, you start summing areas of the load diagram and the shear diagram, and it relates to each other. So this is where it becomes powerful. And then if you want to go even further, you can relate deflection to the moment and shear diagram, which in this case, this would be 0, this would be deflecting down, this would be deflecting down and up. So anyway, we'll save that for structural analysis class though. Alright, so that's this example. Hopefully it's helpful. I've also posted 3 other examples, or will post 3 other examples of shear and moment diagrams from a class I taught last semester, and hopefully that'll give you some more things to look at. Alright, so I think we'll call that good for now. Bottom line, for this method, just start drawing some little free body diagrams of this animal, and you can start plotting your points. Take some time, but you can get there. Alright, I'll see you folks Monday, and we'll just pick it up then.